Okay, so today's lecture is on what I would call inverse kinematics, and then we're going to talk about what's called motion editing. And so where we left off last time was talking about forward kinematics of the human body. That was basically like saying, okay, so if I told you where all the joint angles were, I would be able to produce basically the positions of any point on the body that I wanted to, right? So basically, forward kinematics is basically the following, where I have a formula like this that tells me if I tell you the all the joint angles and so on, can you tell me then where are the 3D points on the surface of the body? Okay. And so we kind of talked about that last time, and this function, which I'm kind of leaving deliberately uncomplicated as f, is basically made up of a whole bunch of trigonometry, right? So basically we talked about last time, if I want to know where is the position of my wrist, what I do is first I tell you what is the angle of my shoulder, how long is my forearm, or how long is my upper arm, what's the angle of my elbow, how long is my lower arm, and that tells me where my wrist is, right? So to get any given point on the left-hand side requires me to go through a whole bunch of cosines and sines and limb lengths and so on the right-hand side. On the other hand, a lot of times what we care about in real motion capture scenarios is going the other way, right? So again, think about what we saw at the motion capture studio, right? What you actually see in the motion capture studio are the left-hand side, right? You see some points on the surface of the body, and from that you want to infer what are these joint angles, right? So we're kind of doing the inverse problem. That's why it's called inverse kinematics. The problem is that we can't just take this function and undo it, right? It's not easy to do because there's all these trigonometric functions inside. So it's not like a nice, easy inverse of that function. Instead, we have to do, there are a couple of different ways we can solve this problem. So inverse kinematics is basically estimating theta from r, okay? And there are kind of two different situations that we might be in, okay? One situation is, and these two situations depend on what is the dimension of this and what is the dimension of that. So if we say, for example, let me get my notation straight. So if we say that if r is in, n-dimensional space and theta is in p-dimensional space, then we have basically two situations. One situation is that if n is less than p, right, that means that I have more joint angles than I have observations, right? And that means that the observations don't totally constrain the joint angle positions, right? This is an underdetermined system. And that means that what we're kind of doing is trying to find the best of the many solutions for theta that satisfy the observed positions of r. So this is like the under-constrained situation. And this is like finding the best solution that satisfies, the constraints. The other situation is when n is bigger than p. That means that I have more observations on the body than I do joint angles, and that's an over-constrained situation, right? That means that basically I have too much information and I can't find some thetas that are going to be exactly consistent with all of those observed surface positions. And so in that case, I have to find some sort of optimization algorithm that tells me what is the closest I can get to match the observed body positions to the ones that I would predict with theta. So this is like over-constrained. And in this case, we need to do something that's along the lines of like a least squares solution. And so both of these situations come up in different ways in motion capture problems, right? So the problem where we were looking at in the motion capture lab, where you observe all these markers and you want to infer what the underlying skeleton is, that's probably in this lower case, right? Because we have a lot of markers on the body. And if you count up the number of markers, XYZ positions and a number of degrees of freedom inside the body, I think that you'll find that for many motion capture scenarios, there are more markers than you need. Okay, so that's usually where we're going to be here, and that's the second thing I'm going to talk about. The position, the situation here is more like saying, okay, you know, if I want to get the position on the body to a certain position in the world, then what are the joint angles that accomplish that? So for example, I'll show you a video in just a few minutes where we can say, okay, you know, I've got a human kinematic model, and now I want to reach out and I want to grab this position in space, right? I don't tell you anything else about what the other joints are doing. In that case, I'm really just pinning a couple of positions in 3D space, and I'm asking the rest of the joints to kind of follow along in a realistic way, right? So in that case, maybe I'm only specifying a few nailed down positions in the 3D world, and I have to figure out all the joints that kind of match up with that, right? And so I'll show you a video in a moment that will make that hopefully a little bit more concrete. Okay, so let's talk about kind of the most mathematical way of doing it, and then we'll talk about a little bit more practical ways of doing it, right? So if I was going to approach this problem mathematically, one way to start is what's called inverse differential kinematics. Inverse because we want to undo the relationship between the joint angles and the surface points, and differential because we're going to be taking some derivatives, right? So if I take my formula from here, I take the derivative of both sides with respect to t, right? So basically, the idea is what I have here is actually a series of joint locations over time, right? Because my body is evolving over time, and I want to use that information that there's some sort of temporal coherence, and consequently I observe some points on the surface of the body over time, right? And so if I take the derivative of both sides of the previous equation, what I get is basically dr dt is equal to df d theta dt, right? This is just the chain rule, okay? And so this thing here is called the Jacobian. And kind of what it means is that, you know, again, f is a function that takes the joint angles in Rp and puts them onto 3D positions in Rn. And so what we're kind of doing is we're saying, okay, so that means that the result of this function is some n by 1 vector. And then this df d theta is basically saying, how does every entry of this n by 1 vector depend on each of the p parameters of theta, right? So this is going to be an n by p matrix. Okay. And so, even though I didn't go into it too much last time, the Jacobian, the concept of a Jacobian also comes up when we were talking about bundle adjustment and structure for motion, right? Because we had a similar situation where we had basically every observation of a image point on the image plane, right, xij, depended on the unknown parameters, which were the camera parameters for camera I and the scene parameters for point j, right? So there was, again, this Jacobian. We talked about how the structure of that Jacobian, the sparsity structure, helps us solve bundle adjustment problems more easily. So if you go back, you can see there's another place where we're talking about Jacobians already in class. Okay, and so kind of what I want to do is I want to get the evolution of these things over time. So kind of what I'd like to do is, let me just abbreviate this with J. So if I knew R and I wanted to infer theta, what I could do is kind of just take the inverse, right? What I'd like to be able to do is just move the J over to the left-hand side. The problem is that I don't have an actual inverse of J because J is not a square matrix, right? J is actually going to be, let's assume that, I guess I should say up here, assuming that n is less than p. We're going to start in this case where I have fewer markers than joints. And so in this case, n being less than p means that my Jacobian looks like this. It's kind of like a wider matrix than it is tall, okay? And so I can't take the inverse of that kind of matrix, right? But what I can do is take what's called the pseudo-inverse, right? So the pseudo-inverse is basically kind of like the inverse, except you know, it isn't, well, it satisfies some properties of the inverse, but it doesn't work because it's not square. So I could say, okay, my d theta dt is j, and I'm going to put like a little cross here like this, that's usually what you mean when you say pseudo-inverse. And this is going to be a P by N matrix, and the pseudo-inverse is defined by basically J transpose, let's see here, I guess it's going to be J, I had it right, J transpose, J transpose inverse. Okay, and so in this sense, what I get is, okay, if I take the derivatives of the observed r's, I can get the derivatives of the observed thetas. And so again, one way to think about this is kind of like only one solution that will satisfy all the observed r's because I'm under constrained. And so this solution minimizes this norm, which is kind of like the norm between dr dt and j d theta dt. There are other solutions. There are many solutions that all satisfy the same observed positions. Again, remember, kind of the way to think about this, right, is that, you know, if I think about pinning one point in 3D space, you know, there are some other solutions for the thetas that all get my end effector to the same point in 3D space, right? So you can, and so for example, also, if I'm only pinning one point in space, then my other arm could be flailing around, right? All those are also solutions, right? So this is kind of like saying, what is the one that has a certain kind of minimum norm, you know, characterization? And so then how would I get back to an actual path for theta? So then what I would do is to recover theta of t, I would basically start at known initial position theta of 0 and basically evolve. That would be like saying that theta of t is like where I started, plus I integrate from 0 to t the derivative. Right? I did this for my inverse differential kinematics. This is my starting point. And so it is that if I know where the person started, right? So for example, if I put them in some sort of a known position where I say, okay, stand like this. And you can see that when we were in the motion capture lab, there were a couple of instances where we were basically saying, okay, stand in this known position, right? And then if I know the derivative of things, I can evolve from that initial position, okay? And so, you know, there are some twists on this idea, and so I'm not going to go into the full details of it, but basically this is the kind of thing that you could do when you had just a few pinned constraints, okay? The more common thing that we want to do for the purposes of actually, you know, if I want to estimate that real-time moving skeleton from the live points on the 3D data, is that I would have, you know, when n is greater than p, right, that means that I have more marker points than joints, kind of speaking colloquially. Then what I'm trying to do is I'm trying to find the thetas that match up with the observed r's as best as possible. And that may be that's going to be an over-constraint situation, assuming that I have more information than I really need, okay? And so in that case, what I could do is I could just minimize a cost function that looked something like, okay, I'm going to look at the sum over all of the, you know, I'm going to say, okay, I'm going to say this is the jth observed 3D point. I'm going to try and bring it in line with the trajectory that I observed as close as possible. So this is like saying this is the jth observed marker, and this is like the forward kinematic model for the jth marker. Right? And the idea is I want to try and make those things as close together as possible, right? With the understanding that I may not be able to, you know, exactly nail down all the observed markers in the world, right? You know, and there may be some errors. Now, on top of that, what I could do is say, okay, you know, in addition to just trying to match the markers really well, what I could do is I could put some additional constraints on there, right? So, for example, I could say, okay, you know, I want here's my kinematic model of the sky, right? So what I could do is I could say, okay, I also want the vector, for example, on these two points of the kinematic model to be in the same direction as, this guy is fat, sorry. All right, well, okay, you're going to take this with a grain of salt. So basically what I could say is, okay, I want this vector between here and here, of course this doesn't satisfy it, to match up with the vector on two markers of the human body, right? So I could kind of say, okay, in addition to wanting the points to match up, I also want the, you know, I can say, okay, I put a marker on this part of the surface of the body and this part of the surface of the body, and I want that vector to be parallel to the underlying, you know, what's this forearm going? This is the
Radius and ulna.
radius and ulna. Is that it? Yeah, these guys? Okay.
Radius is ulna.
Okay. So you can kind of say, okay, in addition to just kind of making sure that the points are right, I also want to make sure that these vectors match up, right? And then you could also put some further constraints on saying, okay, so let me just make a list of possible constraints. So one constraint is, you know, observed marker vectors, let's say, this is pretty casual, match underlying limb vectors. That's kind of what I tried to draw here. You know, another one is basically saying, you know, human motion constraints. Right? So what I mean by that is that right now, when I solve this problem, there are no constraints at all on the thetas that I estimate, right, which are the joints. But I know that for a human, there are certain reasonable joint limits, right? So for example, you know, I can't bend my shoulder behind my back very far, right, where I can bend it this way pretty far. And so there have been kind of these biomechanical tables that have measured for the, you know, average human population, what is the range of motion of each of these joints, right? So for example, my elbow can bend, you know, it can get pretty close to straight, but it certainly can't bend the other way, right, unless I'm double jointed or something like that, right? And so what you can say is, okay, for every joint, I also have a natural range of motion. And on top of that, there are kind of coupled ranges of motion, right? So for example, I can bend my knee, you know, however I want, but I can't kind of like simultaneously bend my knee however I want and bend my other knee however I want. There's probably some sort of a coupling between all my joints at once, right? That's a little bit harder to measure in a table, but there are things that exist, right? So for example, I know that if I'm trying to think of a good example, like, I guess my shoulders and my arms are relatively, you know, unconstrained. But I think that, you know, if you think about, think about what you can do with your lower body and then how it restricts the range of motion that you might otherwise be able to do, right? So if I bend my body in one way, it's a lot less comfortable for me to bend my other leg that's not supporting the weight than it is if I'm supporting the weight in a more natural way, right? So you can kind of talk about these, you know, both individually and coupled, let's say. You could also put things like, not necessarily just the position, but also the acceleration, right? Because really what I'm doing is I'm solving for this function of joint angles over time, right? So I know that I can't, like, instantaneously move my arm much faster than a certain rate, right? And so you want to make sure that your skeleton doesn't, like, jump around because you know that you can't move from one place to another. So there's this kind of, like, derivative constraint that says, you know, velocity and acceleration. And these, again, have been measured by studies. And there also might be some sort of like physics-based constraints. Right? So for example, it may be, suppose that you were in, well, I guess you can't really talk about being in 0G, but suppose that you were, well, so when you're walking, right, there's a natural sequence, there's a natural, you know, kind of lowest energy motion that comes from the fact that you are a body with a certain mass, and you could model your bones and limbs as a bunch of springs and weights and stuff like that. And so you can imagine that when you're walking, you know, you're trying to find the lowest energy position at every possible time. And so you could kind of add these physics-based constraints into reconstructing the trajectories. Now that's something that's probably not going to be in the typical realm of a system like we saw last week. I mean, I think that most of the constraints that are probably being imposed on the Vicon system are probably along the lines of, some human motion constraints, some velocity constraints. But even so, like when you saw the legs get mixed up, right? So there's something that obviously, if you were imposing some sort of reasonable human constraints, certainly like physics-based constraints, that should never even have been considered as a possible, configuration. But part of the issue was that what you were seeing before was kind of like instantaneous estimates of the joint positions, right, or the joint angles, so that the user of the mocap system could kind of watch the skeleton moving around in real time. In practice, what you'd want to do is you save all those marker positions, and then you post-process them afterwards to get as good of a set of joint angles and trajectories as possible, right? So so what you saw on the screen is really not necessarily the stopping point of inverse kinematics. Really what you would do is you would feed all that data into a more advanced inverse kinematic solver and watch it go, and see what you got after the fact. Okay. Okay. So the other thing that you can do, hold on one second, wait. Now I'm told this room sucks. So another thing you can do basically is what I would say, learned from observed data. And so what I mean by this is something where you have a model of how humans are naturally likely to move, right? All these things so far are a little bit more, I would say, they're biomechanical, but they're not based on kind of natural human motion. And so what I could do instead is I could say, okay, I'm going to observe lots of people in my mocap studio, and I'm going to figure out, what are natural ranges of what are natural types of motions for humans, and then I can use that model to basically only generate poses that match up with kind of the things I've seen before, right? And so here's kind of a video that explains that idea. This was from Groucho et al. And so what you're seeing here is, this is the effect of if I were to basically pin the white dots, which are the two arms and this leg, and move the red dot around, if I didn't have any sort of model for inverse kinematics, what I'm going to see is these really weird human poses, right? So if you watch the body, here, these are things that are kind of like ragdoll level motion, right? You would never see a person doing that stuff, right? Whereas if you add some learned information from watching people move, you can see that these poses look a lot more like what a person would do if they were stuck in these bizarre situations, right? And so I got the sound off. Basically, here's an example of basically what they did. They recorded lots of mocap data, and then they kind of record in this kind of lower dimensional space where was each pose. And then when they generate new poses, they only allow the algorithm to generate poses that are close to these observed positions. So let me see here. Right, so here what they're doing kind of is they're dragging this point around 2D space, and you can see that every point that they drag corresponds to a different 3D pose, most of which look like this ball throwing position, right? So all these poses are pretty reasonable. And so the idea is that when I generate a new possible set of thetas, I don't allow myself to stray very far from this manifold, right? And so kind of here what you see is like a heat map that tells me how likely is every pose given the training data. I'm not going to play this whole thing, but you can basically train it on different kinds of motions. So you can say, okay, I have a different manifold depending on whether I'm looking at a guy pitching a ball or a guy doing a jump shot, right? And so the idea is that what you could do is learn, this is natural, baseball behavior, this is natural basketball behavior, and then if you know that that's the kind of motion capture data that you've collected, then you can kind of restrict yourself to say, okay, I'm going to apply the basketball model to this basketball mocap and only generate, good, guys shooting hoops. The nice thing about this is that then you can deal with things like if you were to lose markers, this gives you another way to predict what's happening. So let me see here. So here what they're showing basically is, what happens if I simulate the effect of marker dropouts, right? So now if I've got this model for how all the markers are coupled, then I can say, okay, well, what if I were to lose some markers on the body, right? So here they said, okay, I took away all the markers on the entire right-hand arm, and the synthesized motion still looks pretty good because it learns that people walk like this, right, from observing data. And now I take away the entire torso, and now I took away all the legs, and actually what happens is that still, if all I knew were the markers on the feet, if I learn this model of how people move, the rest of the body follows along in a pretty convincing way, right? And so, this is kind of an example of saying, okay, I know that in theory there's nothing mechanically wrong with me walking, like this, right? But no one walks like this. They walk like this, right? And so you can only get that from kind of learning how people really move, right? There's nothing in the, if you go to a physics-based model, you might discover that because of the way your body kind of moves like a pendulum, like we were talking about in the motion capture lab, that your arms naturally swing in this, counterbalanced way, right? But there's nothing that makes that any more uncomfortable for a human than going like this, right? I think that's all I wanted to show out of this. Then what they kind of show is that you can kind of interpolate between, if you wanted to interpolate between catching motion and a basketball motion, you can kind of do that. That's kind of related to what I'm going to talk about next. This is just kind of showing that you can now more realistically drag the positions of 3D points in the world and make the rest of the body follow along if you've learned what's going on. So here they've pinned the feet and they've just specified the motion of the arm, and then all the rest of the joints follow along with what has been learned about typical human motion. And so you can imagine this would be really helpful for a animator. And here this is kind of an example of a 2D to 3D example where they kind of try and pin the joints corresponding to one view of that person in a picture, and they say, okay, for a walker motion, you get a pretty good looking reconstruction, and then this is like the trained basketball model applying it to a picture of a basketball guy. So here they're moving the joints around to kind of match up as well as possible with the 3D picture, right? So one thing to be aware of in these kinds of situations is that, if you apply the wrong model to the data that you have, it's going to look pretty strange, right? So if you have a ballerina and you apply the basketball model or a boxer model, then your reconstructions are going to look really weird, right? Because the ballerina is doing very non-boxer-like behavior, but the boxer model is the only thing that the model's ever seen, right? So one thing that's really careful is that you have to be able to match up, what you learned on with what you're seeing right now. So, like I said, I think that this is probably, this is probably more advanced than what the off-the-shelf motion capture system is going to do for you, right? This is more like post-processing of the motion capture data to, get better and better, better and better constraints. Okay. One other thing I wanted to mention, I guess, while I'm here is that even after you do all that stuff, there may be still some stuff to take care of, and here's one problem that's called foot skate. And so the idea is that if you watch the person's foot here, you'll see that it doesn't really look right. It kind of slides along the ground. You're going to see it on the slowed down motion here in just a second. So watch the feet and see how they kind of slide along the ground in a way that is not realistic, right? Once you put your foot down, it can't, move around that freely. And so what you really want is something where the reconstructed motion has the person really clearly planting their feet on the ground, right? No skitter around, right? You can't just, so you can't have a motion capture guy who looks like Michael Jackson, moonwalking across the floor, right? You need to have something where they really come down on the ground. And so I think that there's another video here. These are from Lucas Kovar. I think there was, where was the other foot skate one? Yes, here's another foot skate example where you can see as this person comes towards the camera, or this is the original motion, they're going to do something we're going to talk about next, which is basically trying to move that onto a different. But here you can really see the foot skate, right? You can see this person is kind of like, is kind of skating along the floor with their feet, right? And instead, you want to apply some additional constraints to say, okay, that person needs to plant their feet on the floor, right? Their feet can't penetrate the floor, and they can't move once they're planted on the floor. So you kind of pay attention to when does the foot hit the ground, right? And so that's kind of an additional, additional consideration. So I guess I'll also say here, foot skate. Okay. All right, so any questions or comments about this chunk? Okay, so the next thing I want to talk about is what I call motion editing. No, I don't call it, what is called motion editing, right? And so what I mean by that is that, motion capture sessions are inevitably kind of short, right? Like, it's not like you have somebody who acts out a 10-minute scene in a motion capture studio and then you just go back and you apply that to a character in a movie or in a video game, right? More likely what you're asking someone to do, let's think about video games for a second. So what you're probably asking someone to do is, okay, give me a good punch, right? Okay, now give me 10 of those, right? Now I want you to kind of throw this guy over your shoulder, right? So what you're doing is you're collecting a whole bunch of shorter mocap sequences, and then you want to kind of string those together, as one example, into a fluid sequence, right? So if you're playing a fighting game on your PC, you're seeing a lot of motion captured video that is strung together in a way that you don't notice the transitions between different capture sequences, right? And the same thing is probably true for, for characters in movies that have been motion captured, right? So one example that someone was talking about when I visited was along the lines of saying, okay, suppose that you've got two characters that are kind of like walking across the room to shake hands with each other, right? And so in that case, now suppose that I'm going to make one of them a giant like Gandalf and one of them smaller like a hobbit, right? And so now, if I think about what I've actually captured, right, if I scale all that data down, the Hobbit is going to, so say the Hobbit originally took 4 steps to meet Gandalf. Now if the Hobbit is, 0.8 as big, he's not even going to get to Gandalf by the time he has to shake the hand, right? So somewhere you have to add some additional walk cycles in there, right? And so what you may say is, okay, you capture a bunch of examples of, okay, just walk across the room for me a bunch of times, and you splice in walk cycles from other mocap sessions to make it look like you've got the full thing, right? And so kind of what I would say is, there are these things I would call motion blending or interpolation, where we have basically two motions and we want to put them together in a realistic way. And then another option is what would be called motion path editing. And so what I mean here is something where, again, at the time that something is filmed, you don't necessarily know exactly how you're going to use that mocap data in your finished product, right? And so say that you capture somebody who is like, walking in a straight line, but then you say, okay, actually, I don't want them to walk in a straight line in my finished product. I need them to kind of walk off to the left, right? And so now I have to kind of transform that video to, or that mocap data to conform with the path I need them to take in the real world, right? And so what we're going to basically do then is, assuming that we already have these theta i's, right? This is like my captured trajectory. Kind of what I'm doing in some sense, in the easiest sense, is I'm transforming these over into some new, positions over time, right? And so the easiest thing I could do would be to say, okay, for example, I can, I can make each of these guys be a linear function of what I had before, right? So, for example, what I could do is I could, so one example, this would be kind of like a simple filter on the, if I wanted to amplify or decrease the motion of a joint, what I could do is I could change this A of t to attenuate or amplify what's going on, right? So if I wanted to kind of observe someone walking, right, like this, and then I wanted to make them appear more cartoony, what I might do is I might kind of just turn all the joints up by 1.2, and then that person's going to look kind of like over-exaggerated. And I haven't really recorded them doing that. All I'm doing is I'm changing the application of these joint angles, right? So you could do some kind of fun things like that. The other thing you could do is kind of, you can imagine filtering these joint angles to do like slowing down or speeding up effects, right? So if I know that I've gotten from, if I've done this kind of punch, right, and I've observed 30 frames of that, I could interpolate those thetas to get 60 frames of a slow motion punch, right, just by kind of interpolating between adjacent thetas. So, you can basically do anything that you want to these captured joint angles, and you can get some kind of fun-looking motions like that. You're starting to kind of stray from what actually was captured, but for just kind of simple motion tune-up, that's a pretty straightforward thing to do. So, kind of a more natural or a more common thing to want to do is something like this, where you have a couple of motion capture sequences at the top, like a walking motion and a running motion, and you want to stitch those together, but you don't want them to immediately kind of stick together like a hard edge, right? In some sense, what you want is that there's this nice smooth transition between, the person walking, and before they start to run, they begin to kind of jog into the run, right? So you kind of want something where instead of going from, motion A to motion B just butted up against each other, you have this kind of nice transition where I am interpolating from one to the other, right? And so how do I get the person to kind of jog naturally, between the walk and the run? And so kind of the way I think about this is it's kind of like a dynamic programming problem, where you say, okay, I've got to sync up the frames as well as possible between motion 1 and motion 2, and then over the overlap, I can kind of smoothly interpolate between the joint angles, right? And so, for example, here's what I could do. I could say, okay, if I have a cost function that says how close is frame I from motion 1 to frame J of motion 2, how can I find kind of like the best path to match up frame to frame this chunk of motion, right? And so really it is what I would call a dynamic programming problem. Sometimes you hear this called dynamic time warping, the idea being that there may be more frames in image 1 than there are in image 2. So for example, if this bottom motion was a walking motion and the vertical motion was a running motion, then basically you can imagine that over one cycle of left foot to left foot, right? It takes the walker maybe 20 frames to do that, and it takes the runner 10 frames to do that because they're moving faster, right? So what I'm doing is I'm kind of trying to match up as best as possible which of these 10 frames match up as well as possible with these 20 frames, right? And so one big consideration for that might be, for example, looking at where the feet came down. So here what I'm showing is that, when the foot comes down, there's this black dot, right? And so for certain, I want to, make sure that the black dots match up between the two sequences, because you might say, okay, what I'm going to do is I'm going to match the interval between these two foot plants to this longer interval between foot plants, and then I'm going to generate, I'm going to kind of interpolate between the short amount of time it takes the walker between foot plants and the longer amount of time, well, not time, but space, right? So this is like physical space covered in some sense. So I kind of want to make the person kind of move their feet gradually faster as I interpolate between the motions. And so really, that's nothing more than kind of a problem where you say, okay, I have a cost function that says how similar, so I have a cost function on poses that says, okay, so here, this is kind of like, this is the cost of like a matching path between pose sequence 1 and pose sequence 2. And so what I might say is, I have a cost between, the vector of joint angles at this time and the vector of joint angles from the other motion at this other time. And what I'm trying to do is I'm trying to minimize the overall cost between the poses at any given point in time, right? So the idea is that I kind of say, okay, if I have a cost function that tells me, how similar are two poses, like two instantaneous poses. and I kind of sum that up over all the matching along the graph, right? This is exactly the kind of thing that you can do with dynamic programming fairly easily, okay? One thing to keep in mind is that when I try and match these things up, so this could be as simple as, let me just say, this could be as simple as like, you know, sum of square differences. Maybe not the best idea, but it could be done like this. So one thing to keep in mind is that, again, think about how we talked about parameterizing the forward kinematics, right? So that's like saying, okay, you know, this joint angle is always measured with respect to the root of the body, right? The root is this kind of 3D point inside your pelvis, probably, that kind of says, okay, you know, this is the orientation and the position of the person. So all these joint angles are kind of relative to that root. So that's like saying, okay, I don't really care about the 3D angle in some coordinate system in space. All I care about is what it's like relative to the body, right? So if I'm positioned like this, and then I compare it to somebody who's kind of positioned like this, the fact that we're looking in different directions and our body is pointing a different way shouldn't make a big difference in terms of saying, are my elbow and my shoulder joints lined up the right way, right? So this is all kind of like, these are all relative angles from the forward kinematics. With respect to the root. And so once I've gotten the correspondence, how do I actually do the interpolation, right? So now I kind of say, okay, well, I've got the, you know, angle from this person and the angle from that person, and I want to kind of smoothly warp between them. So to actually interpolate between, you know, two poses, well, then what we have here is kind of an issue of trying to interpolate between angles or rotation matrices, right? And so the best way to do that is what's called spherical linear interpolation, or SLIRP. And so part of the idea is that, you know, put simply, if I'm thinking about, you know, how do I interpolate between two poses, right? There are all these rotation matrices and translation vectors tied up in that question, right? And so if I have a rotation matrix that describes, you know, one joint angle, and I have another rotation matrix over here, I don't want to just like average, so say I want a halfway position, I don't want to average two rotation matrices, right? That doesn't work, because the reason is it doesn't give me a rotation matrix. So what do I think about this is that, suppose I have a circle, and I want to average this point on the circle, this point on the circle, you know, that gives me this point, and that's not on the circle anymore, right? What I want to do is I want to interpolate in such a way that I'm always staying on the circle. And so that means I kind of want to go halfway from this point to this point over here along the circle, right? And so this is a kind of a sketchy way of saying that I don't want to just average rotation matrices. I want to find a way where if I go halfway from one to the other, I'm always continuing to be a rotation matrix. And if I were to plot that path, it would kind of look like taking a great circle along the surface of my globe instead of cutting through the center of the globe, right? And so that's one of the homework problems is I give you rotation matrix 1, rotation matrix 2. What you do is you turn them into quaternions, and then you apply this spherical linear interpolation formula to the quaternions. You get a new quaternion, and you turn that back into a rotation matrix, right? That's the best way to do it. And so I'm not going to give away, you know, the rest of it, but that's basically one of the homework problems is to figure out how to do that. It's just a kind of a coordinate, you know, transformation problem. And so let me show you a couple of videos just to show kind of like how this process works. So here's a video that kind of, again, from Lucas Kovar that shows time warping. And so the idea is that, you know, if I didn't time warp between two motions and I just were to directly interpolate between corresponding, you know, positions in time, you would see that the interpolation will look really weird, right? So like, that was like bad interpolation. Let's go back and see that again. So if I'm interpolating from walk to run, you see that over that transition, the person kind of does this weird, like, feet together hop that is physically implausible, right? Right, so that kind of weirdo skip is not something that you would ever see. Whereas if you time warp, that's kind of like showing that there's this nice, you know, so here you're seeing basically effective time warping between different kinds of motions. Running, sneaking, you know. And I believe these are like different interpolations, you know, between different positions. I think the main thing I wanted to show, let's see that again, is the time warping. So basically, you know, if you do it right, there's this nice gradual speed up. And there are some other pictures. Let me show you this one. So basically, here what you're going to see is basically transitions between different motions. So you say, okay, here's motion number 1, guy walking around. Motion number 2, guy walking like a crazy crab for some reason. And now what you're doing here is you're saying, okay, this is where I want the crazy crab motion to start, and then I move this guy and say this is where I want the transition to take place, and then this algorithm basically puts these two together, does the dynamic time warping, and says, okay, now what I've got is, you know, neural walking motion and then smoothly transitioning into crazy crab motion, right? And I believe this is another example of interpolations. So it's like saying you've got two different kicks, you know, different ways of interpolating between those two different kicks that all look like reasonable looking kicks in different ways, right? So it's kind of like saying, you know, these are all kind of newly generated kicks that are built from just those two originals. Like, you know, here's breakdancing guy 1, you know, handspring guy 2, and then what you get are these kinds of interpolations between, you know, the motions that all look like reasonable looking intermediate motions. And so again, you could imagine that this would be handy if you were doing something along the lines of, you know, authoring a video game where you didn't want to capture like 100 kicks. You basically said, okay, instead what I want to do is I want to capture 10 kicks, and then the kick I do on day, you know, on the moment is some combination of these 10 kicks that doesn't look quite like what the person has seen before. So you kind of can mix it up by interpolating. And this is kind of similar. We're going to show this in just a second, but you know, here's an idea where they're pushing this guy around depending on kind of real-time motion, and what you're seeing is interpolation between different styles and also along different paths. And so we're going to talk about that in just a second. And let's see what else. This is just a kind of a picture showing that what you need to do is align the coordinate frame. So if I just were to take the input motions, that if I would just kind of average those coordinate frames, what I would see is this guy who kind of like suddenly walks in place in this weird way and then he flips around. Right? What you want to do is you want to kind of get something where the average of the blue guys is the red guy, right? And you do that with properly aligned the coordinate frames before you do the interpolation. Okay, so let me talk a little bit about this notion of path editing, okay? And so one thing is that, well, okay, before I talk about path editing, let me talk about motion graphs. So motion graphs, again, this is from Kovar et al. The idea here is that, okay, you know, I've got all this motion capture data that I've collected. Now I want to kind of find the best ways to string them together in as realistic a way as possible, right? And so this is like realistically stringing together motions from a library. And so kind of one thing that I want to think about is, well, where is the best transition point to go from one motion to the other, right? So I'm still going to do a little bit of blending between the motions probably, but to make my life easier, what I want to do is I want to find the points where it's most imperceptible to go from motion 1 to motion 2, right? And if I've got a lot of motions in my library, I should be able to do that. And so here's kind of a picture of I guess actually this is just kind of pictures from what I was showing you before. So here's kind of an idea where saying, okay, you know, what I do is I build this set of possible transitions, right? That's like saying, okay, well, certainly here the white dots are like frames from the mocap, okay? And certainly between any pair of adjacent frames from the same captured sequence, I know that those naturally go together, right? Because they were captured from the same person. So there are kind of arrows between every pair of adjacent frames, but then there also may be some points where actually this frame transitions nicely into this one. And so I can draw an arrow that says, hey, you know, this actually would be a reasonable place to jump from this motion over to that motion. And what I can do is I can kind of build, so here the light gray lines are like all sorts of possible transitions, and the dark gray lines are places that I can kind of naturally jump from one to the other without you noticing, right? And so if I wanted to take a path through this graph, what I might say is, okay, I take a little bit from motion 1, I jump over and interpolate to this point in motion 2, I move here, I jump over to this point in motion 3, I go along on that for a little while, I go back to motion 2, I loop around back to motion 1 and go through this again. So basically you can kind of find your way through the different actual captured mocap points. You know, if you do that right, if you kind of assess how similar are any two given poses, you can do that in a kind of realistic looking way. And so here's kind of a sketch of saying, okay, you know, what I do is I look for between frames in one sequence and frames in their sequence, I have a cost function that says how similar are those two things. And the places where this cost function is really low, right? So think about this as white is like a bump and black is like a hollow, right? And so the places where this thing is really low means the cost function is really pretty good to transition between this point in frame 1 and this point in frame 2. And so that can also be kind of periodic in the sense that, you know, if you imagine that one of these motions is like walking and one of the motions is like running, that's natural. I think there are lots of points where I could drop from one motion of walking into the other motion of running. Basically every time that I've got like a foot that goes down is a good point for me to say, okay, that pose actually looks pretty similar to the other guy. I can swap over to there. So the idea is that, you know, when I'm transitioning between frames from the same video sequence, I just kind of play them back in order. When I'm transitioning between frames from different video sequences, I do this interpolation to make sure that I don't have this weird, you know, skittering step that we fixed with our motion interpolation from before. And so, right, so kind of what I would say is that, you know, the idea is to build a graph between all frames from all motions, and then what you could say is kind of walk along the edges of the graph, corresponding to good transitions. And then kind of the final thing that you can do is you can kind of combine these things to, you know, or you can extend these things. I can kind of like walk along predefined paths while doing certain motions. So let me show you a couple of videos about that. Right, so here's the idea is that, you know, you have one captured motion like this, and now you want to make that person walk in a different direction, right? So you can do that with some of these techniques we talked about. Here, I think that the yellow is the direction, is the, you know, the path that the user dragged, and the black is what you can actually do with the data that you have. And then here you see that you're kind of making that person walk a path that you never actually collected in real life, but you're stringing together, you know, bunches of cycles from this observed motion to make it look pretty natural, right? And you can see that this person can kind of do these abrupt loop-de-loops and turns and stuff like that. Or you could make them, you know, here the guy is fighting his way along the hello, right? So you've got lots of kickboxing data that you're stringing together to make the person kickbox along a certain path. And then here's an example where, you know, not only are you going along a certain path, but you are saying, okay, when you're yellow, walk normally. And then when you're green, you know, sneak around, right? And then when you're blue, I'm not sure what happens when you're blue. We'll find out.
Crab.
Crazy crab. No, kickbox, right? And so again, you can kind of basically draw on the floor what you want to happen, and then as you pass the right point, you kind of smoothly transition into doing the next thing. And so these are all basically strung together shorter motion clips that, you know, are estimated to match up well with each other, and then also kind of transformed so that you never see kind of this really bad transition. So you do all sorts of goofy stuff like this, right?
Is that Donatello?
Is it a turtle? It could be a Teenage Mutant Ninja Turtle, yes. And so, you know, there are lots of ways to kind of extend this idea. I think that probably, you know, as you can read about in the kind of interview part of the chapter, there are lots of times when you have to do something to the mocap data that you capture. It's not really that typical to just immediately take what came from the mocap studio and map it onto this character, because, you know, you may be planning what that character does 6 months after you captured the mocap, and all of a sudden, you know, instead of having, you know, 3 sword fights, you're going to have 2 instead. So you have to kind of change the captured mocap data to fit what the narrative of the story is, what the vision of the story is, right? And so, you know, you're definitely in the process. You're definitely in a position of having to do a lot of mocap editing, you know, all the time in real productions. And certainly, I think the stuff I've talked about here is really relevant to stuff like video game design of mocap, where you are clearly seeing these motions of these video game characters that look pretty realistic, but obviously you can't predict what all these motions that you need to do on the fly as a player is moving around need to be, right? So if I am playing, you know, something like Skyrim with lots of people moving around, you know, if I shove somebody, they have to be able to kind of like move realistically and then keep on moving along with their day, right? Even though you never necessarily recorded, you know, shove, right? You have to kind of figure out, okay, I'm going to push them over this way a little bit and see what happens, right? Yeah, so it's interesting stuff. Okay, so any questions about stuff?
Well, actually, that
Yeah.
answered it in terms of this can be done in real time a little bit.
Can it be done in real time? I mean, I don't think the interpolation is that bad. So basically what you do is you pre-compute. Yes, actually, it can be done in real time for sure in video games, right? So basically you've got a whole list of pre-computed motions, and then you're kind of on the fly toggling between them and interpolating between them to make sure they look good, right? So I certainly don't know anything about exactly how it happens under the hood, but video games are proof that you can basically do mocaps, you know, editing in real time. Yeah. The movie stuff, obviously, you're going to spend a lot more time refining all the little subtle motion nuances, because, you know, you can rewind and rewatch a movie, but you can't do that with a video game, right? So if something looks a little bit weird on a video game, you're willing to let it go because you're in the middle of something, right? You're actively participating as opposed to just kind of passively watching and picking away at how bad it looks. Yeah. Other questions? So what I want to talk about next time is a couple things. One is facial motion capture, right? So all the stuff we talked about so far is pretty much body motion capture, right? Like if you remember from the mocap visit we had last week, there were no markers on the face, right? It was only these headband markers that gave me coarse positions of the head. So what do you do when you've got someone's face that you want to capture? And so we'll talk a little bit about how that works with markers, although it turns out that in the real world, a lot of facial stuff is not done with markers in quite the same way. The other thing I want to talk about is, can you do this kind of joint estimation without having someone go into the skin-tight bodysuit with the goofy ping pong balls? I mean, is there a way to do it with purely video-based, normal street clothes, what I would call markerless motion capture? And so certainly that's been a big area of interest in the computer vision community for a long time, is, you know, look at a video, find people, and find out what they're doing, right? So I mean, there are some things from computer vision that you can transfer over to do this kind of markerless motion capture. It's not as good by any means as marker motion capture, but it's still got its uses. So we'll talk a little bit about how far you can go without the markers. Okay, so with that, I will shut myself down here.